some properties of determinant. So let us see the first property. The first property is interchanging rows with columns of a determinant. Now we take a second order determinant. This property holds for any order of determinant, but for easy to understand, we take the second order determinant. But remember that it holds for any order of determinant. Now what do we do? Interchanging rows with columns. That means here first row is the first row AB, the first column AB goes as the first row. B was here, AB was the first column, it goes as the first row, and the first row was AC. If that moves to the first column, so AC was the first row, now it is the first column, and AB was the first column, now it is the first row. In another view we may see this like this is the original determinant and this is another determinant. Now see what is the change, and the AC was the first row here. Now here on another matrix AC is the first column, so first row has changed into the first column, and the first column was AB, which has changed into the first row. Similarly, the CD was the first the second column, now CD is the second row, and BD was the second row, it has become the first column. Now we have seen given a equal sign between these two determinants. Why? Suppose now if we calculate the value of this determinant, it gives AD minus BC, it also gives AD minus BC, so both the determinant has the same value, so these are equal. So we may conclude about this property, thus interchanging the rows and columns doesn't change the value of the determinant. Though we have changed the rows into the columns, the value is equal, and this property holds for any order determinant, be it the third order determinant or fourth order determinant, any order determinant, this property holds. Now come to the second property. This property is interchanging two rows and columns. In the first property we changed all the rows and the columns, and rows into columns and columns into rows, but in this property we are interchanging any two rows or any two columns. Suppose we take a determinant like this is also second order determinant. Now we are changing the columns, suppose, so AC is the first column, so AC the first column goes to the second place, and BD is the second column, it comes to the first place. So we have interchanged the first column and the second column. Now the original determinant was this ABCD. Now what would be the difference or the similarity between these two determinants about their values? They would be equal but with a minus sign. Now let us take the similar determinant ABCD. Now we are changing two rows. Suppose this row AB goes to the second row and the CD row goes to first row, then this value of this determinant is would be the negative of the original determinant. So in both cases, if we interchange two columns or two rows, the value becomes negative of the original value of the determinant. So we conclude that interchanging any two rows or columns of a determinant, the value becomes the negative of the previous value, that means the original value, only a negative sign comes. Okay, now we see the third property. The third property is two rows and columns are same. If two rows and columns are same of a determinant, suppose this is a determinant and we see that these two rows are equal, ABC, ABC, these two rows are equal. We take another determinant of order 3. here we see the first two columns are equal. This is AEG, this column is also AEG. Then their value would be equal and the value would be equal to 0 in each case. This is true for any two rows or any two columns. Here we have given example of equaling these two rows or these two columns, but you may find the value of the determinants by equating any two rows or any two columns, and in each case that would be equal to 0. So in this property we may tell that if any two rows or columns become same, if any two rows or columns become same, then the value of the determinant is 0, is always 0 if two rows or two columns become same. Now the fourth property is this. Fourth property is multiplying any constant k to the determinant. So we are multiplying k to a determinant. Suppose this is a second order determinant a, b, c, d, and k is multiplying to this. So we may write it like this. That means this k is multiplied to the first row of the column. You may multiply it to the second row of the column, or you may multiply it to any column of the determinant. I have multiplied it to the first column, you may multiply it to the second column. So multiplying k to any row or column of a determinant is similar to multiplying the value of the determinant by k. Any row, you may multiply k by any row or any column. It is actually similar to multiplying the k to this determinant. Now the fifth property is addition of two determinants. So what is addition of, how would I add two determinants? Suppose there is a clause there of same order. So if we are adding two determinants, then those determinants should be of same order. If they are not of same order, then we cannot add them. So we have taken this and we are adding this with this. See this, the second and third row, and here the second and third row are equal. So in this case we may add them up. If they are not equal, then we cannot add. So only the first row is unequal. So the result would be the unequal row would get added component wise. That is, the first component would be added to the second component, b would be added with b1, and c would be added with c1, and the remaining two rows which are equal would remain the same. So this is the rule for adding two determinants. This rule also applies if two columns are equal. If two columns are equal and one column is different, then the different columns would be added component wise and the equal columns would remain the same. Now the sixth property is multiplying any row or column with a constant k and then adding it to another row. This is very important property of determinant, because applying this property we may expand a determinant or find the value of a determinant without expanding it through minor or cofactors. Suppose we have taken a second order determinant. For easier understanding, we have taken the second order determinant. Now this is a, b, c, d. Now suppose we multiplying any row or column with a constant k. Now suppose we are multiplying k with the second row, so this becomes kc and kd, and now we have those kc and kd is added to the first row. Then what happens to the value of the determinant? The original determinant was this, and this would be equal to that original determinant. That means we are first multiplying k with the second row and then add them up with the first row. This gives no change in the value of the determinant. Now see this for a so the value remains unchanged here. Now see this for a third order determinant. Third order determinant means this, and if we make a similar operation, we may get like this. Here D, E, F and G, H, I are unchanged, and we have changed only the first row. So how could we change that? Just multiplied M with the third row and K with the second row and add them up with the first row. Then the value is unchanged, because here the value always remain the same. So these are 6 properties. Then the 6th property is very important for determining the value of the determinant.